Okay, so this is another one of our summary videos here for things that we really want to know as we move forward in preparing for this test. And this will be the last one I'm going to make because we got to the end of the content. The last major theme is reaction spontaneity and the so-called second law of thermodynamics. Now, that second law, quantitatively, you all will recognize it as the Gibbs free energy relationship. Okay, but the second law, I guess in words, if I was to say it in words, the second law of thermodynamics is that all spontaneous processes increase the entropy of the universe. And in the lecture when we talked about that, we derived an equation for the Gibbs free energy change. And of course, that equation to you all looks something like this, okay, where the delta G is equal to the delta H minus the T delta S. And the beauty of all of this was that these terms that we derived have to do with the reaction system itself, Rxn. We don't have to worry about the universe, the surroundings, and so on and so forth. We can define an equation that's based and rooted in the reaction under study, the reaction system. So this was kind of our Gibbs free energy equation. Now, remember, for the reaction to be spontaneous, or like we like to say, it happens as written, right? What did the value of delta G have to be? It had to be negative for the spontaneous process. Okay, so when you do the calculation, if you get a negative number, that reaction is spontaneous as written. Now, if it's positive, the opposite's true, and we'd say it's non-spontaneous as written. So this was our Gibbs free energy equation. So you're going to want to know to be able to work problems using that equation, and there are really several different types. Okay. One type of problem that you might face might just ask you, under a very specific set of conditions, is the reaction spontaneous or not? And to answer that, you always calculate your delta G. If it's negative, it's spontaneous. If it's positive, it's non-spontaneous as written. Okay, so that's one type of problem. Another type of problem might ask you what temperature a reaction will become spontaneous. And that temperature dependence, of course, is built into this equation because over here on the right, we have a T term. Remember, that's our Kelvin temperature. Okay, so in such a problem where you're trying to figure out what temperature is the key temperature to become spontaneous or not, what you basically do is you go in and you set this delta G to 0, which is kind of our point where it becomes spontaneous or not, basically, whether it becomes positive or negative number. And then you would solve the equation for your T, based on the information for your delta H and your delta S. And that T then becomes that crucial temperature where the reaction might switch between being spontaneous or not. Now, there's another type of problem. These are sometimes qualitative, but you want to have a general understanding how enthalpy and entropy change for a given reaction, contribute to it being spontaneous or not. So let's take a look at that real fast, okay? So if we look at this equation for our second law relationship more closely, we see that there's two of these change terms over on the right side. There's the delta H and there's the delta S. Okay, this first one, of course, is our enthalpy change. And this second one, we learned about that this semester in this chapter. That's our entropy change for a reaction, right? So looking at the form of this equation, we'd really like our delta G over on the left to be negative for a spontaneous process. In fact, it has to be negative. So what about the sign on delta H then? Well, if delta H is a negative number, that really contributes to spontaneity, doesn't it? In other words, if we have a reaction which is exothermic, that's good for spontaneity. On the other hand, what if our delta H is positive? What if it's an endothermic reaction? It turns out if delta H is positive and we have an endothermic reaction, that's actually bad for spontaneity because it tends to make this delta G positive. All right? So that's not so good for spontaneity. But there's always this interplay between delta H, our enthalpy of reaction, and our entropy of reaction over here on the right. There's always this interplay, right? Because look what we have to do. We take our entropy and we multiply it by the Kelvin temperature. So if I have a reaction where delta S is a positive number, my entropy of the reaction is positive. Looks like the entropy increases because the entropy change is positive. Now if I multiply that by a larger and larger Kelvin temperature, the second term in my equation becomes bigger and bigger and bigger. And notice that we're subtracting that second term, aren't we? So as that second term becomes bigger and bigger and bigger, my delta G would become more likely to be negative if delta S is positive. All right. So at some point, even if I have a positive delta H, I can overcome that if my delta S is positive. All right. So, generally, positive entropy changes are good for spontaneity. So just kind of know, how these enthalpy and entropy changes, whether it's positive or negative, contribute to the process being spontaneous or not. And honestly, if you understand this equation, just the mathematics of it and the form, right, that we subtract this T delta S, you can kind of reason it out, right, based on what the signs are on delta H and delta S. It's usually not too hard. Now, the last thing that I want to highlight here, and I want to erase this so you can read it better, is the last bulleted point. I think we showed a sample problem for this in the last lecture, which was last Thursday. But there is an equation and an approach that chemists can use to interrelate the change in Gibbs free energy for a reaction, or our delta G. That delta G, if we know it, we can actually interrelate that with another concept that we spent a lot of time on this semester, and that's our equilibrium constant K. So I want you to look at a few sample problems. There's one I'm going to link here that allows us to convert this Gibbs free energy change for a reaction that we've learned about in this chapter to our equilibrium constant K. Now, we've been talking about equilibrium constants all semester. And fortunately, there's an equation that allows us to, again, interrelate these things, okay? And that equation is delta G is equal to minus RT times the natural log of our equilibrium constant, KEQ. That's kind of the base form. Now sometimes you might want to solve for KEQ, right? So can we rearrange this equation to allow us to solve for that? I'm writing letters backwards, right? So can we solve for KEQ? And sure enough we can by taking the anti-natural log, okay? And that involves the number E, which is the base for natural logarithms. And what we need to do is we need to take that number E, it's just a number about 2.71. You'll usually find a button on your calculator for E. It's usually second function ln, okay? But we need to take that number E and raise it to the power negative delta G over RT. Now remember, T in this equation is our Kelvin temperature. Always Kelvin, okay? And R in this equation is our gas constant. It's the value of 8.3145, and joules are the units that are attached to that, okay? So when you plug in units up here for your delta G, you want that to be in the joule units as well. All right. But nonetheless, we can relate equilibrium constant to our delta G for a particular reaction. And that's actually a pretty interesting thing, right? Because delta G tells us the spontaneity of the reaction as it's written. Will it proceed or not as it's written? And our K tells us the position of a particular equilibrium, whether it lies with the reactants or products, right? So it's interesting to relate the two. All right, so these are kind of the major concepts I think you need to know for Thursday.